Okay, guys, here we are, and we are going to solve this pre-class warm-up worksheet question here having to do with natural abundance of isotopes. This one's a little bit trickier than some of the other ones that we've done, and so I want to give you those tools so that you can recognize why it's tricky and how to solve trickier problems. So we have magnesium 24 that has its atomic weight. We have magnesium 25 that has its atomic weight. And this is the tricky part, we now have magnesium 26 that also has its atomic weight. And so out of the problems that we've solved to this point have only had 2 naturally occurring isotopes, but this one has 3. So how do you take into account these 3 different isotopes to solve for the natural abundance of 2 of them? So I'm first going to organize my information just like we've done in the past. We have magnesium 24 that has an atomic weight of 23.985, and I'm going to let its natural abundance be X. So that's one of the things that we have to solve for. We also have magnesium 25 that has an atomic weight of 24.986. I'm going to let that be Y. That natural abundance of that isotope is Y. But we have the third naturally occurring isotope, magnesium 26. It weighs 25.983, and it has a natural abundance of 11.01%, which that natural abundance as a decimal is 0.1101. So this is still going to be 2 equations with 2 unknowns, but we've got to be more careful about how we set up those 2 equations with 2 unknowns. Before I do that, I want to just kind of take a double check and see if we can make some kind of prediction for which isotope we're going to have the most of. The weighted average is 24.305. So that means the one isotope that we have the most of is going to be the one closest to 24.305. So that means that we should have the most of the magnesium 24. Its atomic weight is 23.985. That's closest to 24.305. We should have the most of that. Okay, so now we're going to have our 2 equations with our 2 unknowns. First off, you need to recognize that the natural abundance of all 3 of them, when added together, have to give 100%. That means that X plus Y plus 0.1101 equals 1. All 3 of those natural abundances as decimals added together should give us our overall 100%. It's not just X plus Y equals 1. That's only if there's 2. Since we have 3 naturally occurring isotopes, X plus Y plus 0.1101 equals 1. I'm going to go ahead and solve for Y here so that when I write my other equation I can plug it in. So subtract the 0.1101 from both sides, subtract X from both sides, you get Y is equal to 0.8899 minus X. So that's my one equation. So that's the first tricky part of this. When there are 3 naturally occurring isotopes, it's not just X plus Y equals 1. X plus Y plus something equals 1. The next part of this that's tricky is writing the next equation, where we do the equation for the weighted average. So we take the 23.985, which is the weight of the magnesium 24, times its natural abundance as a decimal, X, plus 24.986 times its natural abundance as a decimal, which is Y, plus 25.983 times its natural abundance as a decimal. You can't forget it. It's still important. And those added together, 24.305, I'm sorry. Those added together give you our overall weighted average. So those are our 2 equations with 2 unknowns. This is half the battle. Now I'm going to go through and solve the algebra. First thing I'm going to do is I'm going to plug that in there for Y. And then this, I'm going to do multiply it together. So I'm going to bring down that 23.985x plus 24.986 times 0.8899 minus x plus 2.8607 equals 24.305. Next, I am going to distribute 23.985x plus 24.9, I'm sorry, 24.986 times 0.8899 is 22.235 minus 24.986x plus 2.8607 equals 24.305. The reason I screwed up is because I got a notification on my computer, and so I got distracted. But here we go. Now that we're to this point, we are going to combine the like terms. So here we have 23.985x minus 24.986x. That gives us negative 1.001x. And then our other like terms, we have 22.235, 2.8607. We're going to subtract both of those from 24.305. That gives us negative 0.7907. Divide both sides by the negative 0.1001, and you get x is 0.7899. So stop and think about what that means. We're trying to solve for the natural abundance of both of these isotopes. That 0.7899 is 78.99%. That's how much we have of the magnesium 24. And we suggested, or we predicted, that the magnesium 24 should be the most. And sure enough, it is. It's almost 80% of the total is magnesium 24. We have 11% is the magnesium 26. The rest of it has to be the magnesium 25. So the percent that we have of the magnesium 25, you just subtract those two percentages from 100, and you get that it is equal to 10%. All right, so again, the most important chemistry part of this is that all of the natural abundances for all of the isotopes have to add together to give 100%. So the amount as a decimal of magnesium 24 plus the amount as a decimal of magnesium 25 plus the amount as a decimal of magnesium 26, all of those have to add together to give 1. Then the second part of this, the other hard part of this, is recognizing how to write a weighted average. The mass of the magnesium 24 times its natural abundance as a decimal, plus the mass of 1 magnesium 25 times its percent as a decimal, plus the mass of 26 times its percent as a decimal. All of that added together gives you the overall weighted average. All right, moving right along. Now we're going to get into waves. So we're going to calculate the wavelength of green light in nanometers. That has a frequency of 5.31 times 10 to the 8 megahertz. So this is where these equations become really important. The first equation we had was C equals lambda times nu. C is the speed of light in a vacuum. That equals the wavelength times the frequency. Since the speed of light is 3 times 10 to the 8th meters per second, that means that the units on wavelength has to be in meters. The units on frequency have to be in a 1 over seconds. And a 1 over seconds is exactly equal to a hertz. The other equation that is important for waves is E equals h nu. Energy is equal to Planck's constant times the frequency. So just looking at this, knowing what our equations are, we just need the C equals lambda nu one. We're calculating wavelength, we're given frequency. So the relationship between wavelength and frequency is given by the speed of light. We've got to be careful about our units. So using 3 times 10 to the 8th meters per second, first we're going to have to convert megahertz to hertz. So we have 5.31 times 10 to the 8th megahertz. 1 megahertz is equivalent to 1 times 10 to the 6th hertz. There's a million megahertz in a hertz. That gives us 5.31 times 10 to the 14th hertz. That's the same thing as saying 5.31 times 10 to the 14th, 1 over seconds. A hertz is the same as a 1 over seconds. So now we have hertz. We're going to plug it into the equation to solve for wavelength. So 3 times 10 to the 8th meters per second equals the wavelength times 5.31 times 10 to the 14th, 1 over seconds. Divide both sides by 5.31 times 10 to the 14th. That gives you that sorry, I'm just looking at my notes. The wavelength then is equal to 5.65 times 10 to the minus 7th. And worrying about units, the units on this are going to be left in units of meters. Be careful. That's not what I was asking for. I was asking for the wavelength in nanometers. So we're going to go one step further. Every 1 meter is 1 times 10 to the 9th nanometers. That gives you a wavelength of 565 nanometers. And that's why nanometers are used, because the wavelengths of visible light, they're just really nice 3-digit numbers when we deal with nanometers. And then last but certainly not least, we're going to calculate the energy in joules of 1 photon of that green light. So if we remember what that green light was, it was 565 nanometers. That is its wavelength. And it had a frequency of 5.31 times 10 to the 14th, 1 over seconds, or hertz. So this is where now we're going to get into our energy equation. Energy is equal to Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the minus 34th joule seconds. That means that our frequency has to be 1 over seconds. So you always go back to the units on the constant that tell you the units of everything else. So the frequency has to be in the 1 over seconds, which is exactly equivalent to a hertz. So the energy of 1 photon of this light is 6.626 times 10 to the minus 34th joule seconds times 5.31 times 10 to the 14th, 1 over seconds. So this is why it cancels now. A 1 over second cancels with a second. Our energy units are going to be left in terms of joules, which is what we want. So now we just do that math. 6.626 times 10 to the minus 34th times 5.31 times 10 to the 14th gives us that the energy of 1 photon of this light is 3.52 times 10 to the minus 19th joules.